Welcome to Tech to Tech presented by KYZEN, where we will explore common cleaning questions and answers. Let's get started. I would like to introduce KYZEN's own Dr. Adam Klett.
Thank you, William, for the introduction, and thank you all for tuning into this week's case study. Today, we're going to be talking about the chemical compatibility of thermal interface materials. So what is a thermal interface material? Well, a thermal interface material, or a TIM, is a material that's used in many electronic devices to help improve the heat transfer between two surfaces. A lot of times, it's put between a processor or a component that generates a lot of heat and a heat sink, and that's to improve the thermal performance of the device. These materials work by filling in the gaps and the irregularities between the component that's generating the heat and the heat sink to improve the thermal conductivity of that gap and to reduce that thermal resistance, therefore improving the overall thermal improvements of that device. They're found in many different applications, such as automotive electronics, medical devices, telecommunications equipment, consumer electronics like your phones and things like that. And then even in aerospace and defense systems, things like planes, rockets, jets, submarines, radios. I mean, they're pretty much everywhere. A lot of these TIM materials are based on a silicone components, although there are commercially available TIMs that are not. But silicone materials are chosen for a couple of reasons. First of all, they can be filled with an electrically insulating but thermally conductive filler. A lot of times these are like a ceramic, like boron nitride or metallic oxides, things like that. And they have a great working temperature range. For example, silicones can be utilized down to around -200 degrees C up to around 300 degrees C with no worries of thermal degradation. They also have very good thermal conductivity. A lot of the good products out there that are commercially available can range between 2 and 10 watts per meter K, which makes them very useful for transferring heat away from components that generate. And they can be applied in a lot of different ways. They come in many different forms. They can come in pastes that can be dispensed. They come in pads that can be preformed to the right size that can just be placed on top of the components. And they also have multiple curing mechanisms. You can find TIMs that require a thermal cure, or maybe a TIMs that require a two-part mixture that requires a room temperature cure, maybe a moisture cure, or some that don't even require a cure at all. And so there's a lot of materials out there that you can choose from to meet your process needs. However, silicone materials do have a few issues with them, and one of the biggest is the chemical compatibility issues that might lead to a loss of thermal performance. This can come in the form of swelling, where the material can actually soak up a solvent like heptane or your cleaning chemistry, and then cause the material to swell, and then you lose thermal properties. The solvent can also extract components out of the TIM, which causes also a loss of thermal properties. And then in some cases, you might even get chemical reactions that can again lead to a loss in thermal performance. So it's very important to understand the effect that these different chemistries can have on your TIMS material before choosing them. And in this particular case study, that's what we're going to talk about. We had a customer that came to us for assistance in choosing a TIM material based on its compatibility with their processes. So whenever we have chemical compatibility testing like this, we always like to do two types of tests. The first is a static test, and you can think of this as a benchtop lab test done in the lab in beakers, where the material is exposed or immersed into the solvent of choice. It can be agitated or heated if needed, and this provides good bulk data for material compatibility, but it doesn't take into account actual process equipment parameters. You can see on the top right here, there are two samples that we received in this case. They're pad materials. They're labeled A and B, and we'd like to test, or we were asked to test the static compatibility of these materials. So even if a material passes static testing and it seems to have good bulk material compatibility, we also recommend dynamic testing. And dynamic testing actually takes into account the process variables of the actual equipment that are used. For example, inline cleaners or ultrasonic or whatever it may be. This accounts for things like the pressure that the material will experience, flow rates, temperatures, rinsability that may happen, exhaust, exposure time, all the things that can't be taken account in the beaker on the benchtop. Generally speaking, this is a little more harsh than the static testing because it does have, higher pressures, higher temperatures, higher mechanical forces, and things like that. However, it is generally more representative of the end use case. And so, like I said, even if a material passes static testing, we always recommend doing dynamic testing in the application to make sure that it meets those requirements. For the dynamic testing in this particular case study, we have a sample that you can see on the bottom right. There was a silicon die that was attached to a metal substrate via the TIMS material, almost like an adhesive. And you can see it kind of oozing out of the edges there. So the static testing test is it's very simple. The first thing that we do is we take an FTIR spectrum of the sample, and it's a Fourier transform infrared spectroscopy spectrum. For those of you who aren't familiar with FTIR, we're essentially looking at the chemical makeup of the material to see if there are any changes. So we'll want to take a pre-test spectrum and then a post-test spectrum to make sure that the chemistry of the material hasn't changed much. So we'll start the test off by taking this, pre-test spectrum, and then we'll weigh the samples to get the mass of them. And then what we're going to be doing is we're going to be immersing those samples in the solvent or the appropriate chemistry for the prescribed amount of time, and seeing how much of the chemistry absorbs into the material or how much of the material dissolves into the chemistry. After the prescribed amount of time, the samples are removed, they're rinsed, they're dried, and then we weigh them again and we test to see how much mass the sample gained or lost. We'll then do a post-test FTIR analysis to look at the changes between the chemistry of the tested and bare samples. So let's look at the data. In this particular case, the gravimetric analysis, or the masses of the samples, showed very little change over the course of the time period tested. So the table on the bottom right shows the two materials that were tested. In this case, it was the Micronox MX2322 and the Aquinox A4727 were the products that were being evaluated. And the different columns represent the different amounts of time that the samples were submersed. In this case, we tested times between 10 minutes and 120 minutes. And again, if we look at the data, there's very little change at all. Most of them are less than 1%. And for the ones that are greater than 1% change, they're not much greater. So this is good news to us because it indicates that these materials show good compatibility with both of the cleaning chemistries that were tested. So if we move on to the FTIR data, again, the table on the bottom right shows what we're going to call the correlation between the received sample and the tested sample. So each of the rows represents a different sample, either tested in the MX2322 at different time periods, or in the A4727 tested at different time periods. The first column represents the sample A, or the material A, and what we're looking at is the correlation or the difference between the as received sample and the tested sample. The closer to that correlation number is to 1, the less it has changed. And so, or basically, the lower that number is, the more it has changed. So what we want to see are numbers very high, as close to 1 as possible. In the first column, for sample A, we see that in both cases, in both the 2322 and in the 4727, we see very high correlations, which means that there's little to no difference between the as received material and the tested material. If we look at material B in the second column, we see a very similar story with the 4727 on the bottom right. Those 4 rows show us that the correlations are very close to 1 and that there's no chemical change in the material between the as received and the tested material. But if we look at the correlation of sample B to the as received for the MX2322, we do see that over time, that correlation does start to drop, which tells us that there might be some chemical changes that are happening over the course of about 2 hours. All right, so like I said, once we do static testing, it's always good to do the dynamic testing as well to see if the machine parameters and process parameters change the compatibility of the sample. So in this case, we do something very similar where we start off with an FTIR analysis of the tests to make sure that nothing is chemically changed between the as received and the processed material. We then weigh the samples, and then the samples are exposed to the appropriate chemistries, but in their appropriate machines. So for example, in this case, the Aquinox A4727 was used in a spray and air inline washer. and the Micronox MX2322 was used in an ultrasonic tank. In both of these cases, the samples were processed for 15 minutes, and then they're taken out, dried, weighed again, and then a post-test FTIR analysis was done to look at the change in the chemistry. So if we look at the dynamic testing data, the gravimetric results are very promising and very similar to the static tests, where we see that there's little to no change across the two samples that were tested in either case. And this makes sense because if you look at the sample there on the bottom right, there's very little surface area that is actually exposed to the chemistry, which is a good thing in a lot of these cases because it doesn't allow the chemistry to reach the middle or the bulk of the material. And so we see very little weight change in our sample as well. And this lines up with the static testing as well. So if we look at the FTIR results, we see something very similar that we did with the static testing. The correlations between the as tested and received samples are very high, very close to 1, which is very good, which means that there is very little to no chemical changes happening in the sample, which signifies good chemical compatibility. Now, remember from the static testing, we saw a decrease in the correlation with the MX2322. However, remember that this test, the dynamic test, was only done for about 15 minutes, and only the edges of the sample were exposed to the chemistry. And so in this particular instance, the dynamic testing might actually be less harsh than the static testing, which is good because this means that in this actual process, there should be no problems with this chemistry if this particular tin material was chosen. All right, so in conclusion, we were able to carry out the short-term compatibility testing of all 3 of the tin materials that were provided by the customer, and we were able to make a recommendation as to which material they should use. In this particular instance, all 3 of the materials that they were trying to choose between showed very good chemical compatibility given the process parameters. And so in general, KaiZen can support your selection of TIMS materials or the cleaning solution depending on your needs and your processes. All right, so here are a couple frequently asked questions on this topic. So the first one is, can I put assemblies with silicone materials like these TIMS into my inline cleaner? Generally, we like to say no unless testing like this has been done, because there are chemistries that will dissolve and extract things out of those TIMS materials, and you can end up building that up in your inline cleaner or batch cleaner, whichever it may be, and then that might cause issues down the road for you. And so if you've done these tests and you've qualified and verified that there are no issues, then it's fine. But if not, we highly recommend you to not do that. And the second question is, how can I verify the chemical compatibility of TIMS with my process or your process? And it's a very similar process to what I just described. Right? We recommend the static and the dynamic testing to see how the material behaves on its own in a bulk sense. And then we also like to make sure that we also test the dynamic testing, which does take into account your specific process parameters. The other thing to note is that if you have any special needs or properties that you need to verify or keep keep a check on, for example, any thermal properties or maybe RF properties that are important to your application, you probably need to track those as well. So taking before and after measurements to make sure that, let's say, for example, the dielectric constant doesn't change if you're interested in that. And then the last question I have here is, would compatibility testing be similar for pastes? As you saw in this particular case study, we tested pads, but as I mentioned, these thermal interface materials come in a variety of forms and methods, and a lot of people use dispensable pastes, and the answer to the question is yes. The simple answer is yes. There might be a slight difference in the logistics on how to transfer the materials between vials and things like that to make sure that you don't lose any artificially lose any material when you're doing your weights and balances and things like that. But in general, it's a very, very similar process. All right, so those are our frequently asked questions, and that's the end of this case study. And then I'll turn it back over to William. Thank you.
Thank you, Dr. Adam, and thank you guys for watching this Tech to Tech session. If you'd like to discuss this topic further or have any questions not answered in the session, please contact your local KaiZen regional manager or send an email to tech@kaizen.com, and we will have someone follow up with you as soon as possible. To download the case study this session was based on, click the link in the description. Do you want to have exclusive access to future content sent directly to your inbox, or do you know someone who'd benefit from these sessions? If the answer is yes, just go to tech2tech.kaizen.com, fill out the subscription form. And if you like this video, be sure to follow us on our social media platforms for more expert cleaning content.